Okay, welcome back to homework 10. This video will cover the first three problems of homework 10, which review 555 timers. These are the first three. And let's start with the first one. So the first problem says, consider a 555 timer below in time delay mode. That is very important. So let's underline that. Time delay mode. What value of R do you need so that the output of the timer will stay at a high voltage for 1 second after the trigger goes low? So for this problem, it's not super tricky what we need to do. All we have to do is realize that this is in time delay mode and go look at the notes. So let me pull up the notes, and we can see that in here we have time delay design equations, and we have this boxed equation, and this is the only equation that we need for this problem. So we will take that back over to the homework, and we'll write that down. So we'll say T, oh, it's kind of thick. Let me make that a little thinner. There we go. So T is equal to 1.1 times RA times C. And in this problem, we know that we want the time to be 1 second, so we'll plug in a 1 there. And we know that the capacitance is 2.2 times 10 to the negative 6th. And we don't know RA, so you plug those in and you solve this equation, and you're done with problem number 1. Not super hard. So let's move on. Let's see if we can scroll down to number 2. So number 2 is a little bit more complicated because now we are in oscillator mode. So this problem says consider the 555 timer below configured in oscillator mode. What value of R do you need so that the output oscillates at 500 or 150 kilohertz? And at that frequency, what is the duty cycle of the oscillator? So for this one, same thing, we just need to go into the notes and find the equations that we think are most useful. So let's go back to this page. And so now, if we take a look at this, this is our 555 timer in oscillator mode. And these are the equations which correspond to that. And what we'll notice is RA is the resistor on top, and RB is the resistor on bottom. And in our problem, this one will be RA, and this one will be RB in all of our equations, as well as the capacitor will be C. So if we look here, we'll notice that the equations that will be most useful to us are the frequency equation here, as well as the duty cycle equation there. And so what I'll do is I'll go back to the notes and I will write those down for us. So let's solve for the first one. So let's see. Whoops. So the first one, we're gonna write down the equation. So F is equal to 1 all over 0.693 times RA plus 2RB multiplied by C. And we know that this is 150,000. We know that this is 5,000. And we know that this is 220 pico, which is 10, about that Siri, 10 to the minus 12th. So all you have to do is solve this equation for RB, and that will give you the resistance that you need up here for R. So the next part of the question says, at that frequency, what is the duty cycle of the oscillator? So to do this, we just need to use this duty cycle equation from before. But before we do that, let's talk about what a duty cycle is. And so up here in the notes, there is a smaller equation right here that says that the duty cycle is equal to the T high divided by the period times 100%. And so all that means is the duty cycle is the percent of time that a signal is in its high state. So if we have a signal like this one up here, so in the output of this one, we notice that the T high is longer than T low, and so that means that this duty cycle should be more than 50%. And this drawing might not be perfect, but the idea behind it is that if it were exactly even, so I'll draw one that's even, I'll do that in red. If it was, oh, that didn't switch to red, sorry. If it were exactly even, so pretend that those are even, then this duty cycle would be 50%, because half of the time of each period, because this is a period, half of each period is high and half is low, and the duty cycle is just the percent of time that a signal is high compared to low. And so we're finding the percent of time that this certain frequency in this oscillation is high. And so what we'll do is we'll go back to here and we will grab this equation and we'll bring it over to our notes. So let me write that down for us. So we have duty cycle is equal to RA plus RB divided by RA plus 2 RB, and then we multiply by 100% to turn it into a percentage. And so after you solve for RB in this problem, and you already have RA, you just plug those in to their respective locations in this problem, and you will get the value of the duty cycle. Okay, so not too bad on that one. The next one is the trickier of the three problems, so let's see if we can get down to that one. So problem 3. So in problem 3, the only difference between this one and the last one is now there is something called a diode. So let's read through the question on this one. It says, the circuit below shows a 555 timer in oscillator mode. However, it is slightly modified by putting an ideal diode in parallel with RB. And so that ideal diode is, let me get this pen set up. The ideal diode is just right over here. And it says, with this modification, what are the new equations for the period of oscillation, T, and the duty cycle? So if you go back to the notes, let me remove some of these markings that I made earlier. So in this box, what we notice is they take the period and they, here, let's zoom in on this. Oops. They take the period and they use that to solve for T. And so this is the new equation. We're going to derive a new version of that equation. And as well, we're going to derive a new version of this equation. And what we notice is that both of these include, so T, I'll box this in red. So T is made up of T high and T low. And these are the equations for T high and T low. And duty cycle is made up of T high as well as the time over here that we're going to solve for. So we need to solve first for the period, and then we can use the period and T high to solve for the duty cycle. And so what we need to do is figure out, okay, what is going to change in these two equations that will affect these derivations of these equations. And so let's go back to this. And so the couple things that you need to know about this is that T high uses the resistance normally in the equation RA plus RB, and you will notice that in the equation. But this is just the resistance between the 5 volts. I'll draw an arrow to show 5 volts to the trigger. Sorry for the sloppy handwriting. So 5 volts to the trigger. But if we look at the picture, I'll do this in green. 5 volts to the trigger, we go from 5 volts down through RA, and now instead of just passing through RB like we normally would, we have this diode over here. So we need to understand how will that diode affect this resistance. So for those of you that don't know how diodes work, Diodes are basically like a one-way wire. So if we have a diode, so this will be our diode, this means that in this direction going down, the resistance is equal to 0. But if we were going up, the resistance would be equal to infinity. So essentially, it just allows current to flow in one direction for free, and in the other direction, it can't flow. So it's like an open in one direction and a short in the other direction. So if we use that knowledge to solve for this problem, let me erase some of this green stuff up here. So we know that we want to go from 5 volts to the trigger. So that means we're going to have to pass through RA. So if we're going to write our new equation, I'll put a star here. This will be our new equation for the resistance from the 5 volts to the trigger. It will be RA plus, and then when we get to this node up here, we can go through the resistor or through the diode. But like we just talked about, going down through the diode, this way will have 0 resistance. And because it has 0 resistance, these two will combine in parallel to equal 0. And so the new equation for T high, instead of using RA plus RB, we'll just use RA. So let's go grab that equation. So it's T high is equal to 0.693 times RA, and this RB will go away times C. So let's write that down. T high is equal to 0.693 times RA times C. And that's it. So now we have to find the equation for T low. So T low is going to use the resistance. It normally just uses RA, which is the resistance from the trigger to the discharge. So if we look at this, oh, I apologize. This should be not RA, but it should be RB right here. Let me just replace that. So T low uses RB, and we can see that in here. T low uses RB. And so we want to find the resistance from the trigger to the discharge. And so let me remove some of these markings from before. So if we're going from trigger to discharge, here is the trigger, and here is discharge. To go from those 2 points, we have to go through RB and this resistor, or I guess this diode in reverse. But like we talked about, going through the diode in this direction has an infinite resistance, or acts like an open. So the resistance from the trigger to the discharge, which is connected right here, will just be equal to RB. So the equation for T low is the same as before. Okay? So hopefully that makes sense for you guys. So now if we look at this, the derivations, let me just remove some of these markings up here. So the only differences that we make is that now this RB is gone. So now this RB is gone, and then when we combine these two, this 2 will go away. And then over here, that change will propagate up to here. And I'll let you guys solve for the duty cycle, but it shouldn't be super tricky if you can follow this order. Okay, well, I think that is all for the first 3 problems. The next video will have the rest of the homework assignment.